All right, well, welcome back, everybody. Here, I thought I'd come here from shooting my class here from Mars. So there's a shot from Mars right behind me here. Okay, all right, well, let's see where we're at. We ended up on chapter 8. And before I do that, I want to make sure that you are aware that you have access to what is called Study Mate, okay? Now, if you go to your class on Canvas on the left-hand side, let me go back there again. Make sure Canvas has been acting up this morning. I don't know what's going on here. Okay, here we go. And so when you get into your class on the far left, there's something called Study Mate. There's a link that when you click that, there's another link right here I'm pointing to called Nomenclature Practice for you. When you click on that, it opens up a new tab and this pops up. So the two things that work pretty good, I think, given that Study Mate doesn't understand parentheses, is using the flashcards and or the matching. You can try the others, see how it works out for you. But flashcard works good. Now there's 140 some combinations. Let me click on the flashcard. And so here we have this one called phosphorus trichloride. We're going to talk about the molecular compounds, the covalent compounds, and how to name them. But phosphorus trichloride tells me this is P3 chlorides, 3Cl. I can flip it, and there's the formula. Remember, it doesn't support subscript, so that 3 after the Cl is a subscript, okay? All right, so you got 143 chemical names. So what does that mean? That even though as you proceed with it, you can do mix and match. Here's lead 2 sulfide, okay? There's the formula. And so while you're doing this, you see lead sulfide, but that could have been easily lead chloride. Okay, so you have approximately about 20,000 combinations here. Only 143 are shown, but as you progress, you can keep in mind that every cation I can substitute any different anion and vice versa. So with 143 is roughly about 20,000 different combinations that you can do. Okay, the other choice is. Let me go back to it. Come on. Oh. Is the matching. I like this pretty good. Here's the name, nitrogen monoxide. And so you got nitrogen monoxide, meaning one oxygen, one nitrogen. Okay. And so that would be the formula. So you got choices here that you can select from. Go on to the next question. So lead or nitrite, okay? Remember, we have nitrate, nitrite. So that's a good tool for you, an additional tool to help you out with respect to the naming. Okay, so this brings us to chapter 8. We ended up on chapter 5. Slide 15, we're just beginning to talk about variable ionic compounds with variable charge, but we ended up with names of the polyatomic ions, which we get from the table. And a reminder there that is that we don't change the name of the polyatomic ion. It's the name, we just leave it at that. And if we need more than one of the polyatomic ion, we put a parentheses like we have there with hydroxide. Here, calcium hydroxide. We need 2 of them because each hydroxide has a -1. And calcium ion, knowing that it comes from group 2, when it becomes ionic, has a +2 charge. Okay? So, which brings us to the variable. Now, I mentioned to you the 16 constant charge ions, 16, 100% of the time. That meant that the other metals have a variable charge. In fact, they can vary from +1 to a +9. Okay, so in order to write those properly or to identify them, we use Roman numerals. Okay, Roman numeral I, capital I, represents +1. IX represents +9. Okay, and then we continue with the anion that we change its name and give it the IDE. This aspect about the IDE, the anion part, that also continues forward when we start talking about covalent compound naming. That part of the naming continues even though they're not ionic. Okay. All right. So in this case, we need to first figure out the charge. Well, we don't know what it is, just the way it's written. So we need to calculate it. We calculate it because I gave you that general formula that said total number of cations plus the total number of anions must equal 0. Okay. I also said that the total number of anions plus the total number of total number of cations plus the total number of anions must equal the overall charge of the molecule. And in this case, the overall charge of the molecule is 0. That's a more general, more broad equation that you can remember because sometimes you may be asked to figure out the oxidation number of an element, but it has a charge. Like if you were asked, what is the oxidation number of sulfur in sulfate? And sulfate has a -2 charge, okay, in the sulfate polyatomic ion. And so that's why that equation is a lot broader and more useful. So here it's a neutral species. So we need to calculate what the charges are. And what do we know? We know that the chlorides, okay, each have -1, right? They're going to, chlorine is in group 7. It becomes ionic, picks up 1 electron. It's got a -1. What that tells me is that I have, let me write this down here. You can follow along. That tells me is we don't know what the oxidation number is on copper. Okay, so I leave it as so, but I do know that there are 2 chlorides and each one has a -1 charge. So it gives me a total of -2. And we also know that this formula we were given has a net charge of 0. Okay, so we set up our little general equation there. Copper plus -2 equals 0. We solve for copper, and copper is equal to a +2 charge, right? Because we want them to be equal to 0. That infers that copper must be in the +2 state, obviously, but we use a Roman numeral 2 to name it. Okay, and that is the name of it, copper 2 chloride. So again, you'll always know the oxidation number of either the cation or the anion. Okay, and if you don't know the oxidation number of the anion, if it's hooked up with one of the 16, because you know their oxidation number, you can calculate the anion oxidation number. Okay, does that make sense? For example, what if I were to give you a hypothetical equation and say it is potassium. Now let me do this. Potassium W. W is a hypothetical anion, okay? Hypothetical anion. The question is, what is the oxidation state of W? Okay. Well, we know that K and W are equal 0. There's no charge of it. So I know that potassium is a group 1 ion. So potassium is a +1. Okay. It's a +1 plus W equals 0. Okay. I saw for W, that means that W is a -1 oxidation state. Okay, so in that example, I gave a very generic structure compound name. And you knew the charge of the cation and calculated the charge of the anion. In the copper 2 case, we know the charge or the oxidation number of the chloride, and we calculate the oxidation number of the cation. Okay, so you're always going to know one or the other. All right, so here we got this one here. All right, we got Tb, which is lead, and then we have O2, which is the oxide. All right, so then we set up our systematic approach again. All right, we set up a problem. We got lead, which we don't know because it's not part of the 16, so it's going to have a variable oxidation state. So lead is what we're going to calculate its oxidation state. We know that there are 2 oxygens given the formula. And we also know that being in group 6, oxygen becomes a -2 when it becomes an ion. Plus the name changes to oxide. Since each oxygen is a -2, okay, therefore we have a total of a -4 because the formula we're given is PO2. Now we got that set up. We solve for lead. Obviously, lead here has to be +4. Okay, double check your math, which implies that we're using lead IV, Roman numeral 4. Okay, oxygen becomes, the name becomes oxide as normal as we've been doing. And so the lead is lead, Roman numeral 4, oxide. Okay, see how we work that through? All right, look at this one here. Okay, what do we know about bromine? Bromine, each one has a -1 charge. Okay, so again, we set up our equation and we don't, Ni is nickel, we don't know what that is. Oh, we know that each bromide is a -1, just like the chloride, called the halogens, okay? And there's 3 of them, so we got a -3 here, and that is equal to 0. Now, this may seem redundant, but again, I'm going through a systematic approach, so eventually you get to the point that you can just look at the formula and, there it is. It's going to be a +3. Okay, it has to be. Nickel has to be a +3 to cancel out the -3 of the bromides. And so nickel is Roman numeral 3, name-wise. And that is the nickel that's being used for that formula. So we got nickel, Roman numeral 3, bromine. Okay, manganese. Well, here we have the sulfur. And like I said before, he said, okay, I got the sulfur. You might think sulfide, right? And then immediately following that sulfur, you got an oxygen. Specifically, you got 4 of them. So that indicates a polyatomic ion. So that sends you to the periodic table where you have a listing of all the polyatomic ions, and you look it up and you see that SO4 is the sulfate with a -2 charge, which suggests that Mn, manganese, must be a +2 charge, and it is. Okay, so we go through that scenario, and that is a manganese, Roman numeral 2, sulfate. Remember, we have to use Roman numerals for all the metals that are not those 16. Those other 16, group 1, group 2, and the other 4, aluminum, aluminum, zinc, silver, and cadmium. Those were constant. Those 16 had constant oxidation numbers. So we don't use Roman numerals for them because they're constant. Everyone else has a variable. And hence, we have to use Roman numerals. Here we go with copper, and then we see a nitrogen. We might think like we did with sulfur, so nitride, right? But then immediately following that nitrogen, we get an oxygen. So that again flags you to a polyatomic ion. Specifically, which one? Well, depends how many oxygens. And this one has 3. Look it up on the table. You'll find it to have it's called nitrate. And furthermore, it has a -1 charge. Okay. That means that copper must be a +1 charge, which means that you're using Roman numeral 1. Okay. So this is copper 1 nitrate. Okay. And then finally here, number 5, we got CO, not carbon monoxide now, lowercase o. It's the element, cobalt. Okay. Now you got the nitrogen. Look to immediate right. There's no oxygen after the nitrogen. So that now tells you, I'm dealing with nitride. Okay. Nitride, the single element. And we go look up, we know that nitrogen's in group 5. When it becomes an ion, it gains 3 electrons. Okay. 3 electrons. That implies that cobalt must be in the +3 state here. So this is cobalt +3, Roman numeral 3, nitride. Okay. Nitride. Notice the nitrite and the nitrate. Okay. Hey, red didn't come out very good. The nitrite and the nitrate. The IDE has no oxygen following the nitrogen. The ATE, the 8 and the ITE have oxygen following the nitrogen. You right here? Okay. All right. Let's do it. Oh, yeah, okay. Now here we have, again, we have parentheses. Having parentheses, again, should flag you to say, I got polyatomic ions. You got CO3. Well, which one is that? Well, we go to the periodic table, right? Look in the bottom left corner there. Look for CO3. We got it right here. Even more so, it's got a -2 charge. -2 charge. Okay. And then we go back and it's a little more complicated, but it really isn't. You think about it. Okay. We know that the CO3, the carbonate, has a -2 charge. Okay. There's 3 of them. So that tells you that there is a total of -6. Okay. So let's do this, write it down in the mathematical equation. And so we don't know what iron is, that's what we're trying to figure out. But we have 2 of them, right? See the subscript of iron? So we got 2 of those irons. 2 of them. So I'm going to put the 2 Fe plus the cobalt each have a -2 charge. And in the parentheses tells you there's 3 of them. So that tells me I have a total of a -6. And that is equal to 0. Okay. Now, here's your algebraic equation. Now you solve for it. What is the oxidation number of the iron that we're using here? What would it be? I set up the equation for you. Can you solve for iron? What would that be, guys? Okay, well, let's rearrange this. Let's solve for iron. So we got 2 Fe. I moved the -3 over to the right side of the equation. So I got to add +6 on the left and the +6 on the right. So I end up with 6. +6, okay? So now I got 2F is equal to +6. Now I got to isolate the iron. So iron would be a +3. Anna, that's correct. Seventeen, that's correct. So iron would be F equals A +3 stage oxidation number, based on how we set this up. Okay. Now, what's even more amazing, if you think about it, as I stated earlier, remember when we were putting them together and we had an odd number, we had looking for a common number. And then I said, you know what? The charge of the anion is the, excuse me, let me repeat that. The subscript of the anion, okay? The subscript of the anion becomes, is the charge of the cation. Look at that 3 on the carbonate. And then I said the subscript of the cation, which is the 2 on the iron, is the charge of the anion. Didn't we look that up in the table? You know, and we found out that carbonate each has a -2. Okay, so I could, at a glance, when I got that formula, automatically say we are working with iron 3, just based on the subscript of the anion. Okay, and the mathematical equation we just set up, that just verifies it. So iron must be a +3. So we're dealing with iron, Roman numeral 3, carbonate. Okay. Now, bear in mind, we just did specific examples, but bear in mind, we can take the lead example and hook it up with the bromide. Take the lead, hook it up with the sulfate, the lead with the nitrate, the lead with the nitride, the lead with the carbonate, and do the same with the nickel. Okay, nickel with the oxide, nickel with the sulfide, nickel with the nitrite, nickel with the nitride, nickel with the carbonate, and so on and so forth. Okay, so right now you got what, 36 combinations right there. Okay, so mix it up a little bit. You start learning more and more names. So you essentially can put together any anion and any cation. Okay, you can put them together, so that gives you a large number of compounds, ionic compounds, that you can now have access to. Okay. So earlier I mentioned when we first started this chapter that, you know, you could be able to either, if you're given the formula, find its name, or if you have the name, give its formula. And so here we are. Okay. So here we have SR and OH, OH minus specifically. That is a polyatomic ion. Okay. So we have to look up, if you don't know what it is, OH minus, the fact that it's a charge on it, the fact that there's more than 2 elements in it tells you polyatomic ion. Look that up, and that tells you, and you'll find out that its name is called hydroxide. Okay. Now you're given the element SR. Okay. So you need to determine, first you got to find it on the periodic table. And so we need to find SR, which is strontium. So I'm going to pull up the periodic table. Okay, and look for it. Oh, there it is, number 38. Okay, number 38 as the element. Now, as an ion, we need to figure out the charge. Well, it's in group 2A. All right, so that tells you 2 valence electrons. There's 38 electrons, and those 38, there's 2 of them in the valence shell, specifically in the 5s2 shell. Okay. So, and it's a metal, so it's going to lose 2 electrons. Okay. So you'll end up with a +2 charge. Furthermore, because it's one of the 16, we don't need Roman numerals. Okay. So you got a bunch of information just by finding it in the periodic table. One, you found it in the periodic table, told you how many valence shells it has. When it becomes ionic, that tells you, first of all, let me back up. Find on the periodic table, determine that it's a metal, which tells you it's going to lose electrons. Okay, it's in group 2, so it's going to lose 2 valence electrons, giving you a +2 charge. And then finally, it is part of the 16. So if we have to give it a name, we just simply give it a name. We don't have to work with the Roman numerals. Okay, so all that information is obtained just by its position on the periodic table. And so then we end up with first putting them together. And strontium has, like we just stated, has a +2 charge. Oh, +2 charge when it becomes ionic. All right. And we have the hydroxide, which has a -1 charge. So that means we need 2 hydroxides. Okay, because we want to put them together and cancel out the charge. So our formula. Oh, that was quick. I thought I broke them up. Our formula is SR parentheses OH. Okay. Let's go through each one because I thought I had them separated. All right. So AuCl3. Obviously, we're given the formula. We need to write the name. Au, which is gold, is not part of the 16. So that tells you, okay, I need Roman numerals. The question is, well, which one? Well, what do I know? I know that the chlorides, the anions, right there, each one has a -1 charge as an ion. There's 3 of them. That tells you that the gold we're using must be Roman numeral 3. It must be a +3 charge. So its name is gold, Roman numeral 3 chloride. Okay. Zinc. Zinc is one of the 16, and it has a +2 charge. Oxygen, when it becomes an ion, becomes oxide, has a -2 charge because it's in group 6. Zinc has a +2 charge, okay? And therefore, its formula is ZnO because the +2 and the -2 cancel each other out on a 1-to-1 ratio. And its name is zinc oxide. Zinc oxide. You find that a lot in what do you call it? Diaper rash cream. It's a drying agent. Used quite a bit. All right. Next one, number 4. We have barium and we have the PO4 -3 polyatomic ion. Okay. Send you to the periodic table, look up PO34. Guess what? Its name is phosphate. Okay. And it's got a +3 charge. Now, barium. What charge do we have there? Well, barium is in group 2. It's a metal, but it will lose 2 electrons. And so it has a, let me see if I can draw it here. It has a +2 charge as an ion. And so now we got not an even Steven 1-to-1 or 1-to-3 like that. We got a +2 and a -3. So we need to find a common number. Okay, and that common number is 6, which tells you that I need 3 bariums and 2 phosphates, which gives me the formula Va3, subscript 3, and then parentheses, because we need 2 of the polyatomic ions phosphate. We need 2 of them. So we add a parentheses, and then we put the subscript. Okay. Lithium. Again, we have a polyatomic ion and SO3 -2. So we look that up. The key here is SO3. Okay, so make sure you grab the right one because there are 2 of them. There is a sulfate that has 4 oxygens, and there is a sulfite that has 3 oxygens. Okay, so that's the polyatomic ion. And we know that lithium being in group 1 has a +1 charge when it's ionic. So that means I need 2 lithiums for every sulfite. And so my formula becomes listed there in number 5, Li subscript Q SO3. I don't put a parentheses around the SO3 because I only need 1, okay? All right, aluminum and sulfur. Well, break them into the ions. What do we know about aluminum? Aluminum's in group 3. It's a metal. It's going to lose 3 electrons. You got 3 valence electrons. It has a +3 charge. Sulfur is a nonmetal. It's in group 6. When it becomes ionic, it will pick up 2 electrons to give us that happy 8. Okay, so it ends up with a -2 charge. Plus, the name changes from sulfur to sulfide. And so now we have a charge non-equality, if you will, because we got a +3 and a -2. But we use the same principle. We need to have a common number. And so a common number here would be 6, as we've done before. So we need 2 aluminums ions and 3 sulfide ions to give us the formula Al subscript Q sulfur sub 3. Okay. All right. And then finally, we got just the name. You got Cu, which is copper. And then parentheses again, flags for a polyatomic ion. Go to the table, look up the NO3, which is the nitrate. And furthermore, each one has a -1 charge. And since we got 2 of them, 2 -1s, that infers that the copper must be a +2. Has to be, okay? And so the copper that's being utilized here is copper Roman numeral 2 nitrate. Let me clear it up a little bit so we can see that. Okay, copper 2 nitrate. All right. But again, another thing to take away from this is mix and match. You know, the strontium, we can hook it up with the chloride, hook it up with the oxide, hook it up with a phosphate, combine it with a sulfite, combine it with the sulfide, combine it with the nitrate, and do the same thing with the others. We can do a gold hydroxide, gold oxide, okay, gold phosphate, gold sulfite, gold sulfide, gold nitrate, or the nitrite, any combination thereof. So here we got another 49 combination. All right, so you see we're building it up for the different combinations you can do. Okay, any questions so far? No? All right, well, here we go with this one. Here we got sodium and nitrate. Well, they're asking you to give the formula. So we break it down. All right, so the first one, sodium. What we do is we find out where obviously we need, no, don't want to show you that. We were going to work through it. Okay. All right, we know that sodium is Na. We also know that it has a +1 when it becomes ionic. Okay. Nitrite. The key is the ITE. Okay. That should send you to the polyatomic table. The nitrite, which will come right here. Okay. Here's the nitrite. Okay, you might be tempted to the nitride, IDE, but remember the IDE is the single element itself, whether it be chloride, whether it be oxide, whether it be phosphide, it's always a single. When we start adding the 8 and the ite, we're talking about adding oxygens to that element. So N for nitrogen, ITE for the oxygen, specifically 2 of them. So that's the NO2 negative. Oh, don't forget to remember what the charge is, which is the -1. Okay. Okay, so now we can put down sodium, which is the +1 because it's the group 1. And then we got NO2, right? Negative. So we can very quickly, that's our formula. Sodium, put them combined together. And I know they're all grouped up, but we'll go through each one individually. Okay. So that's our formula then. Nickel, break it down. The Roman numeral tells us that we're dealing with a +3. Okay. The oxide, just by the name itself, oxide. Okay. That is oxide tells you that's the O2, which I wrote down here. We have a dissimilar number of charges, so we find a common factor, which tells us that we're going to need 3 oxides and 2 nickels. Okay, and that's our formula: nickel subscript 2O3. Or you can recognize something here is that that becomes the subscript right here, and this becomes a subscript right here. Okay, nickel 2 O3. So whichever way works for you is fine. Let me clear the drawings. My drawings are getting a little bit crazy. Okay, we got magnesium. We've looked up magnesium. Magnesium is in the +2 because it's a group 2 metal. Iodide, it's a halogen, which means it's an ion. It will have a -1. I always tend to put circles around my charges so I know that I'm dealing with a charge. Okay, that means that I need 2 iodides. And sure enough, that's my formula. All right, the other one, a little bit challenging here, but not too bad actually. Okay, we got aluminum. Aluminum is in group 3. It's a metal. It's going to lose 3 electrons. The cyanide, that's the one that may be a little bit of a problem, but no problem. Shouldn't be a problem because the term itself hopefully would direct you to the polyatomic ions, which are right here. Cyanide, that is the polyatomic ion that you're working with for that problem, CN negative. And so we have aluminum, which is the +3. And then we have the cyanide, which each one has a -1, okay? Which means I need 3 of them. 3 cyanides cancel out the +3 of the aluminum. Hence I utilize the parentheses because again, the polyatomic ion. So I need to put a parentheses right there and subscript 3. All right. Any questions about this? Again, mix and match. I can't overemphasize that. Nickel and the oxide, sodium and the oxide, sodium and iodide, sodium and cyanide, etc., etc. Nickel nitrite, nickel iodide, go on, etc., etc. You can mix and match here. Okay. All right. Someone had a question?
I just had a question about number 2, the nickel oxide. My
Correct.
audio cut out, so I couldn't get the full explanation.
Oh, okay. Well, the thing here, it's written out as nickel. Remember, whoa, went too far. Remember that the Roman numerals, when written out right here, that Roman numeral deals with the oxidation of nickel. And so what that tells you is we're dealing with nickel plus 3. Okay. If that were nickel 2, to be Roman numeral 2, we'd be dealing with nickel plus 2. Okay. So that Roman numeral oxide, the term oxide itself should direct you to the oxygen, obviously for OX, but the IDE tells you that that is the ion of oxygen, which is a -2. We know it's a -2, remember, because it's in group 6. It's going to pick up 2 electrons when it becomes an ion. So when it picks up 2 electrons, it has a -2 charge. Okay. And that would be true for sulfur, who's also in group 6, so that would become sulfide. Oxygen, when it becomes an ion, there's a name change, it becomes oxide. Iodine, for example, like the next number 3, when it becomes an ion, becomes iodide. Notice the similarities here with the IDE. Okay. And so now we got a +3 and a -2 ion that we need to get put together. And so we need to find a common factor. Normally we can just simply put them either 1 to 1 or 1 to 3 or some easy number we can put together. But here we can't easily put a +3 and a -2 together. We have to find a common number. Okay. And in this case, like the examples we've been doing before, the common number is a 3 or 6. Okay, so I need 2 nickel 3s to give me a total of +6. And I need 3 oxides to give me a total of -6 because that equals to 0. Okay, and so that number I wrote in front of the ion becomes the subscript for the compound. You can see on number 2 here, it's nickel 2, subscript 2, and then the oxide subscript 3. So that is the formula. Okay. All right. Any questions on other questions on these? All right. All right. So with respect to ionic compounds, and it's a combination of metal and nonmetal, that's what we've been doing up to date, up to now. For example, number 2, we just simply called it nickel 3 oxide. Okay. And that 3 represented, again, the Roman numeral represented the oxidation state of nickel. When we write the formula, you see there's 2 nickels and 3 oxygens. So we didn't talk about nickel 2 or say dinickel 3 trioxide. We didn't use any prefixes. Okay. The same is true with aluminum cyanide. We said aluminum cyanide, simple as that. We didn't say tricyanide, just aluminum cyanide. The point is, for ionic compounds, that is a combination of metals and nonmetals. We don't use prefixes. Okay. But when we get into molecular compounds, when you have a combination of just simple nonmetals coming together, now we get into prefixes. Okay. And like I said, they're not ions, but they come together and the naming remains the same. So oxygen will be in use for molecular compounds, and its oxide, be it say sodium oxide or carbon dioxide. Okay, it's still oxide. The name stays that way. Okay. Now the prefixes that we use is mono, di, tri, tetra, penta, hexa, hepta, and octa. And we can go 9 and 10, but most of the time we're going to stop here at 10. But 9 would be nana, and 10 would be deca. Okay. the term A, the letter A, like in penta or in tetra, when you combine it with another letter like another, it's an English thing. If you combine, say, tetra and oxide, you're supposed to drop the A if there is a vowel that are being, two vowels are being connected. So A is a vowel, and if I'm connected with oxide, O is a vowel, the A is supposed to drop. But if you forget to do that, I'm not going to count you up for that. So what I'm saying, tetraoxide or tetroxide, take either one. All right, so those are your prefixes, okay? Now, the central atom, its name is whatever its name is from the element. So like we said, carbon dioxide, it stays carbon, right? But the oxygens, the two oxygens remain, the name stays like as if it was an ionic compound, is oxide. So hence carbon dioxide, meaning there are two oxygens. But the first name, first nonmetal, we just give it whatever the name is from the element. And then the second, we change the name again, like we did with the ionic compounds, okay? But in both cases, we add prefixes if necessary. If the first nonmetal is all by itself, we just leave it as carbon, like CO2, for example. Yeah, CO2, for example, this would be simply called carbon dioxide. Okay, we didn't say monocarbon, okay, because the first, like we said, we don't use mono if the first nonmetal is by itself. So carbon is all by itself, so we just say carbon dioxide. Here, we see we're still dealing with carbon, we're still dealing with oxygen, okay? The name carbon oxide, the difference is here, it's one oxygen. So we have to use the prefix carbon monoxide. Notice how that's how we distinguish between the two. If we did not use the prefixes, if we did not use these prefixes, the di and the mono, think about it. The name would be carbon oxide. We got two different compound chemicals here. We got carbon with two oxygens and carbon with one oxygen. We have to distinguish the difference between the two, totally different chemical properties. Okay, just like we did with the variable charge ionic compounds, we had copper 1 and copper 2. In that case, we used Roman numerals. Here, we use the prefixes for covalent compounds to distinguish the different chemicals. All right, let's try another one. Okay, now, my suggestion first is I call it the parent name, okay? We see phosphorus, that is the central atom. In fact, there's two of them, but we'll get to that in a second. And then we got oxygen. And so my suggestion is to first write down the parent name, which would be phosphorus and oxide. Okay, that's the parent name, the base name, if you will. Now, once you got that, because all you got is the phosphorus and the oxygen, okay, now we come back because we recognize that they are covalent compounds. We got to use prefixes. The first phosphorus is not by itself. There's two of them. So here we have to use a prefix. So we have di. And then there are 5 oxygens. So we add pentoxide. And normally it would say the A, but because I'm combining with an vowel, O, I'm supposed to, for English purposes, I guess, rules, drop the A. If you forget to drop the A, don't have a problem with it. Because I find myself forgetting myself. Okay, so what we have here is diphosphorus pentoxide. Okay. Notice that the example there did not drop the A. But grammatically, you're supposed to drop it. Okay. Now, we're starting with formulas and getting to names, but like we did previously for the ionic compounds, keep in mind, you might be given the name, you got to work back to the formula. Okay, so it's a two-way street here. All right, next one. Okay, same scenario, break it down, systematic approach. Okay, we have the phosphorus and we have the fluorine. All right. Wet, but it is bonded. It's not fluorine F2 diatomic. It is bonded to something else. So the name, like in the ionic compounds, becomes fluoride. Same thing. Okay. But we have phosphorus is the parent name, and then we have fluoride. Okay. That is the base name. I call it parent name, the base name. Okay. Now go back and check if you have more than one of each to add the prefixes, and we only have one phosphorus, and it's the first atom, so we don't have to put the mono. Okay. And then we have 3 fluorides, so we can add tri. Okay. Phosphorus, trifluoride. Okay. Here we have the iodine, which is the central atom. So we don't call that iodide. In this case, iodine is a central atom, so we keep the name it has. So it's iodine. And then we have fluoride attached to it. Whoop. I don't know how to spell. Okay, so there's our parent name. Okay. Iodine and fluoride. The IDE tells you that the fluorines or the fluorides are bonded to the iodine. We have 7 of them. Okay, and so that is heptafluoride. Okay. All right. So you see how we do this. You're given the formula, write the parent name, if you will, the base name. All right. And then add the prefixes. This and work it backwards if you're given the name. If you work it backwards, you got, for example, iodine, heptafluoride. Well, you write down the parent structure, iodine and fluoride, and then check the prefixes to tell you how many of each to work backwards. Okay. We'll do that here in a bit. We'll go the other direction. Okay. All right. So the first atom is the central atom, and then followed by whatever is bonded around the central atom. Now, you will get more than one central atom sometimes, okay? It's not always a single atom, but there are examples, many examples of compounds that have multiple central atoms and everything else is bonded around the central atom, given this one here, okay? But don't let it shake you up. It's the same process we've been doing. We got 3 BRs and 8 oxides, okay? No big deal. First thing to do is to write the parent name. So BR is the central atom is written first, so it stays not bromide, but it stays bromine, okay? The IDE, the IDE part, always tells you that that is bonded to the central atom. But when it's an INE, it is the central atom or atoms. So bromine, and then we got oxygen, but it's bonded to the bromines, and we remain with the name of oxide. Okay. So that is the base name. We go back now and put the prefixes. There's 3 bromines. So there's tribromine. And there are 8. Okay, 8 oxygens or oxides, octoxide. Now notice I got an A there, right? So the general rule is when you combine them, you're supposed to drop the A and leave it at that. Octoxide, okay? Or octaoxide. Either one will work for me. All right, next one. Okay, similar scenario. Write down the base name. In this case, we have phosphorus and the sulfur, 7 sulfurs. So those still remain sulfide because they are bonded to, they're written after the first atom. So they are bonded to the central atom, or in this case, atoms. All right. So we have 4 phosphorus, so which is tetra. And then we have 7, which is heptasulfide. Okay. Now let me get rid of some of this stuff here. All right. Excuse me. So you see how we're working it, how we're working this? We're given the formula. Get the parent names first, okay? We got sulfur and oxide. There are 3 oxides, hence the name sulfur dioxide. No different than carbon dioxide, carbon monoxide. Okay. Now, given what you know now, how would you name H2O? Otherwise known as water. What if I needed to give it a scientific name? What would I name it? Well, okay, hydrogen monoxide is almost there. You got it. Add the di to it. Dihydrogen monoxide, because there's 2 hydrogens. Okay, so yeah. Dihydrogen monoxide. That's the one. If you go look up on the internet, they give you some crazy stuff about it. But it's simply water. All right. All right. So you got it. Dihydrogen monoxide. All right. So now you're given the name. Okay. And you're asked to, all right, give me the formula. So like we were doing when we were doing the formula, we came up with the base name and then we added the prefixes. Well, in this case, we first figure out the base formula and then based on the prefixes, add the numbers as a subscript. And so we have here iodine and then hexafluoride. Okay. And so the base formula would be iodine, which is I, and then fluoride, because the IDE tells you that the fluorides are bonded to the iodine. Okay. Now, once you got that, now you go back to the prefixes, and there's no prefix in iodine, so there's only 1 iodine, and there's hexafluoride, meaning there are 6. So this will be subscript 6. So the formula for this one, the first one would be IF6. Okay. All right. Same thing here. figure out the base formula for it first. We got dichlorine pentoxide. And so it's Cl for chlorine and then oxygen. There's our base formula. Go back and check for the prefixes. There are 2 chlorines, excuse me. Okay, so that's my subscript. And penta, meaning there are 5 oxides. So that's our formula. And this one here, again, systematic approach. We got phosphorus and iodide. Phosphorus. And iodide. Okay. That is our parent name. And then we'll go back. Notice there are 2, so that becomes diphosphorus. And finally 4 tetra. Okay. Then, which again, you can tetraiodide. All right, so let me clear this up a little bit. It's getting a little messy there. Getting close to the end of this chapter. So a reminder spot here. Only use the prefixes with the covalent compounds. Okay, just like we did here. Okay, don't mix and match the 2. Ionic compounds have no prefixes, okay? Use the Roman numerals only with those metals that are variable in charge. You know, they're not part of the 16. And so with the 16 ions, metal ions, no Roman numerals. So all the other ones require Roman numerals, so we know specifically which oxidation number we're working with. Because remember, some of these metals have more than one oxidation number. Copper has a +1 or a +2. Iron has a +3 or a +2. They're all different, so we have to distinguish them with Roman numerals. Back in the day, they used to use something we called IC and OUS, cupric and cupris, and that was very, very ambiguous. In fact, some places, sometimes they still continue with that, but the modern way of naming those compounds is going away, and they're gonna, start using Roman numerals to distinguish, because that way, there's a group in chemistry, this international group, that they get together and they figure out the naming of compounds. So everybody's in the standard nomenclature method. And so the chemical that I named, the scientists halfway around the world will know they know what chemical exactly I'm working with. Okay. All right. Roman numerals are only for those variable charge metal compounds. Okay. Polyatomic ions, those are ones in the periodic table. We don't need to change the name. They have their own specific name. So nitrate wouldn't be called, nitrogen something trioxide, something to that order. I've seen all kinds of names for that. Don't do that. Just name nitrate, nitrite. If you need more than one in the formula, use a parentheses, you keep them intact. Okay. So try this one. What do we got here? BaCl2. You got 3 minutes, right? Go. All right. What is the name for BaCl2? Who wants to take that? Go ahead and sound it off. Or type it in. Either way. BaCl2. Uh-oh. 3 minutes coming up. We should be done by now. with the very first one, BaCl2. Okay, we got a cat here. Barium chloride. That's good. That's a good one. That is correct. All right. I don't think I got the answers here, but I won't give the answers yet. About
Barium dichloride.
barium, no dye, remember. Just barium chloride. Barium chloride, it's ionic, no dye, no prefixes on the ionic compound. So as written in the chat by Sienna, that is correct. Barium chloride. How about NO2? First recognize that it is covalent. Therefore, being covalent requires prefixes. Who wants to take a shot at number 2? You can type it in. And don't worry. What's that?
Nitrogen dioxide.
Nitrogen dioxide. That is correct. That is correct. Just like carbon dioxide, but here's nitrogen is the central atom, dioxide. Okay. Number 3. They want the name here. You can first of all recognize number 3 that it is ionic. We got a metal, non-metal, so no prefixes. Second of all, Fe is a metal, obviously, right? It's not part of 16, so you're going to need Roman numerals. So what would be the name for number 3? Okay, and then recognize that parentheses. That parentheses should tell you, polyatomic ion. I got a parentheses around it. So maybe I need to go to the polyatomic ion table and see if I can find a PO4. Iron phosphate. Kiana, you're 50% correct. There you go. Sabrina, yes, but not the numbers 1, the Roman numeral, the letter capital II. So that'll be, yeah, there'll be iron, parentheses, capital I, and parentheses. Okay, but yes, that would be iron 2 phosphate. Okay, what about, yes, exactly. That means number 4. What would be the formula for number 4? Okay, so diiodine tetroxide. Okay, so iodine and oxide, they're both, obviously both, they're using prefixes, so they're covalent compounds. Okay. So what would be the formula? What is do the base formula first. I got iodine and oxide, so it's IO. That is the base formula. Then you look at the prefixes. How many iodines does di have? 2. Exactly. There you go. That will be correct. I2O4. All right. And then not finally, but we got silver and sulfate. Not to be confused with sulfide. IDE would mean sulfur all by itself, but they're talking about 8. So that is something that says, let me go check the periodic table under the polyatomic ions. And you'll find that to be the case, to be SO4 -2. Okay, what do we know about silver? Silver is a metal, sulfate's a non-metal, so we have an ionic compound here. Okay, we don't have to worry about Roman numerals because silver is part of the 16. So what would be the formula for number 5? Silver has the symbol Ag. And sulfate, if you look that up, is SO4 -2. Or what would be the formula? Right there. Okay, because SO4 has a -2. We know silver, each one is a +1, so I need 2 of them. Okay, hence I need a subscript 2 for silver sulfate. There you go. You got it, Sabrina. And then nickel 3, Roman numeral 3 tells you I'm using a nickel +3. The sulfide is a -2. Okay. And being -2, hey there, we have a dissimilar charges here. We got a +3, a -2. We find a common number, and you're going to end up with Ni2S3. Okay. All righty then. Well, that should end our chapter. Oh, let me go back. Double check. Yeah. Okay. Don't forget to do the worksheet. There's a worksheet on chapter 8 that will help you quite a bit with respect to nomenclature. Don't forget the study mate that would help you with naming and writing the formulas for them. And if there's any questions, obviously shoot me an email or bring them to class next time. Okay, and we can go over it. All right. Yeah, we covered the key points about nomenclature. Covalents are the only ones prefixes, and Roman numerals only for the variable charge metals. All right, I got to get my assistant here. She likes being up here. It's toward the end. She knows. All right. Any other questions?